our esteemed guests, we are now going to start the last session of the day, and you're going to be hearing talks and presentations related to information technology, applications of artificial intelligence, computational and data sciences. And I don't want to take much of the time of the panelists. We're going to start with our colleague, Engineer Yusuf Al-Dagar. It gives me great pleasure to invite to the podium a distinguished member of the Bibliotheca Alexandrina family, our colleague, Engineer Yusuf Al-Dagar. He's the director of the International School of Information Science Department at the BA. He joined the BA as a software engineer in 2002, working with Brewster Kahle, Internet Archive founder, to set up the BA's first web archiving computer cluster and continued to lead the BA's effort in web archiving in the years that followed. In 2013, Al-Dagar has also became involved with the BA's supercomputing services. He earned his bachelor degree in computing in 2001 at the New York Institute of Technology, and he was profiled in the Marquis Who's Who in Science and Engineering. Please join me in welcoming Engineer Yusuf.
Thank you very much for the introduction and for the opportunity to speak. I find it really interesting that we are the only library in the world, to our knowledge, that has a supercomputer. I'll come back to that later during my presentation. So as the Library of Alexandria, we have 4 objectives: to be the world's window on Egypt and Egypt's window on the world, to be the library for the digital age, and to be a center for dialogue and tolerance. As the BA ICT sector, we took on the objective to become an instrument for rising up to the challenges of the digital age. So today I would like to highlight some of our projects at the BA ICT and how they relate to the strategy for sustainable development set for Egypt's future for 2030 and beyond. So we find that our projects fall under 3 of the pillars of the strategy. The 3rd pillar, knowledge, innovation, and scientific research. Pillar number 7, education and training. And pillar number 8, culture. So we are a library. And as a library, we have books, but we also have digital books. So very early on, since our inauguration in 2002, we started digitizing books. So we have a facility at the Library of Alexandria called the Digital Lab, where we scan books and other content and turn that into digital form with optical character recognition, full text search, and we put that into a repository. This repository we call the Digital Assets Repository, which is available online at dar.bibalex.org. Currently, it has close to 500,000 books. About half of these are Arabic, and we have over 20 languages. We developed the full system in-house, and we are proud to have this contribution made to the technology domain in Egypt. Other than books, we have also specialized archives. One archive we're very proud of is the memory of modern Egypt. This project documents the period since Muhammad Ali till President Sadat. And it has a collection of various types of items, and this is all available online. Again, this is also was developed in-house by our engineers. We also have presidential archives. So we have an archive for President Gamal Abdel Nasser, a very important era in the history of Egypt, and also of President Anwar Sadat. Those are all, again, available online. 2 works we're proud of have digitized. One is the very famous volumes of Description de l'Egypte. This is a work that documents a lot about Egypt, done by the French campaign by Napoleon Bonaparte. And this was one of the volumes that we digitized very early on at the start of our digitization operation. We also have digitized l'Arab, which is a work by an Egyptologist, a French Egyptologist, who documents the Muslim monuments in Egypt. We are a library, so books are very important to us, and also language is very important to us. So one of the work we do as ICT is we work on the technology of natural language processing, and specifically we're involved with a project known as the Universal Networking Language. It's a project that aims to connect all the naturally spoken languages together and develop technologies on top of that platform. One of our interesting applications is automatic diacritization for Arabic. So Arabic, as a language, makes use of diacritical marks that indicate how letters are pronounced. Many of the text does not come with these marks. So this software allows you to add marks, diacritical marks automatically. This tool is available online. And this tool would have many useful applications, such as enhancing Arabic speech, text-to-speech technology. And this can in turn be used for accessibility and assistive technology. Language is very interesting because as humans, we are a very unique species in how we use language. And speaking of species, we have a project that aims to document all known species to science on the planet. This involves lots of data. This project is known as the Encyclopedia of Life, and as the name states, it attempts to become an encyclopedia of all living things. Not just the basic information about these species, but how they relate to each other and different traits they have. So, like I mentioned, it involves lots of data. We're developing this technology in collaboration with the Smithsonian Institute, and we are proud to have a prototype available online to look at eol.bibalex.org. So speaking of big things, let's talk about the web, the World Wide Web. It's a very big store of information. As a library, we feel we have an obligation to preserve and archive humanity's documentary heritage. And today, a very big part of that heritage is online, is on the web. It defines how we interact with each other and the knowledge we develop over time. So we have very early on at the Library of Alexandria had a web archive. This is a collection of web pages captured through a process known as crawling, which is how we collect information from the internet in an automated way. This project aims to be like an out-of-print store for web pages. It involves lots of data. Currently, we are speaking about storage capacity of about 5 petabytes. This very large store of data has lots of applications, including research. This data can be used as research data sets. This project we started in collaboration with the Internet Archive nonprofit foundation in the United States. And we have a mirror of 10 years of full web crawls. And currently, our focus is on collecting Egyptian and Arabic content. We are the only library in the region that's involved with web archiving, and we feel we have an obligation to preserve that content for the future. We have developed many tools related to web archiving. One tool I'd like to show quickly here is the visualization of the crawl process. This is a tool to draw dynamic graphs that depict how the web is being collected by our automated robots. Speaking of visualization, we have a unit that specializes in visualization and computer graphics, and we have done a lot of work with virtual museums. So we have digitized the BA Antiquities Museum, and we have a 3D space where we can navigate this museum and look at the different artifacts. This software also allows for things that would not be possible in real life, or at least for the casual museum visitor. We can put pieces together, rotate them, make comparison, and further explore the museum. We took this one step further. We developed a tool, a framework called the Virtual Museum Framework. This tool allows non-developers, people without programming skills, to build their own virtual museums. And by the way, this tool was developed as part of European collaboration project we were involved in called VICEM. We have recently been doing several applications in the realm of virtual reality. So this is a technology that we feel will have an impact in the future. So one recent experience we developed is a white cane experience, which aims at explaining how the white cane is used by people who require one, and how we can best shape the environment to be friendly to everyone and accessible for all. Another very interesting virtual reality experience is a virtual cycling experience. This simulates one riding a bicycle on the Corniche of Alexandria. At the beginning of my talk, I mentioned supercomputing, and that we are proud to be the only library that has a supercomputer. We have had one since 2009. And this machine exists for the purpose of supporting scientific research. We feel this project has a strong impact on our community. It gives researchers in universities in Egypt and research institutes the platform they need to perform simulations and advanced computations. This project has been on, this resource has been on high demand, and in 2016, we had an upgrade of the system that brought the capacity of the cluster 10 times the original. Currently, it's capable of performing theoretically up to 118 tera floating point operations per second. That's lots of calculations. It's definitely not the fastest supercomputer on the planet, but we feel it has much bigger impact on our community, like I mentioned, as it provides this resource to our scientists and our researchers who require it in all domains of science today. We have an online portal where researchers can apply for access, and we've also been developing automation for the management of this resource. And this portal is part of that automation. And we look forward in the future to integrating technologies such as artificial intelligence into how we automate this service and provide support to our users. This platform has many applications in all domains of science, including medical applications, physics, bioinformatics, astronomy, vehicle automation, self-driving cars, and again, we feel it's a contribution we are very happy to make to our community. With that, I conclude my talk, and I'll be happy to receive questions at the end of the session. And this is my email address. If anyone is interested in any of the things I mentioned during my talk, I'll be happy to hear from you. Thank you very much.
Thank you, Engineer Youssef. As you said, we're going to postpone the questions to the end of the session so that we can move on to our second panelist. I'm pleased to present a renowned Egyptian scientist who we are all proud of, Professor Hisham Al-Askari. He's a professor of remote sensing and earth system science and director of computation and data science graduate programs at Center of Excellence in the Earth Systems Modeling and Observations at the Schmidt College of Science and Technology at the Chapman University in USA. Professor Al-Askari received his PhD in computational sciences and informatics from George Mason University in 2004. He was named a Game Changer Orange County Leaders Transforming the World by the Orange County Business Council in 2018. In 2019, Professor Al-Askari contributed among 200 scientists worldwide to the IPCC report on the desertification chapter. Please join me in welcoming Professor Al-Askari.
Good afternoon, everybody. It's a great pleasure and honor to be here today. Your Excellencies, Dr. Marwa, thank you so much for the kind introduction, and thanks for the invitation. It's my absolute privilege and honor to be here amongst esteemed colleagues and scientists. It's just heartwarming to be back to my city of origin. I'm from Alexandria originally, so I feel home. I am home, and this is a great feeling. Today, I would like to share some of the work that we have been doing over the past few years in terms of Earth observations addressing key environmental challenges along the Sustainable Development Goals. Today, in the morning sessions and the early afternoon, we have been hearing a lot about very interesting terminologies, and the term complexity came more than once. And for me, that's very interesting and very important, because when we are dealing with a system like this, you can see there are a lot of complex processes which are running between what we call the spheres. And by the term spheres, I like to move around. So I'm not sure if I can get a handheld mic. That would be good. So when we are looking into an animation like this, you will see the term spheres come into play. And by the term spheres, we are referring to the atmosphere, the hydrosphere, the lithosphere, the biosphere, the cryosphere. All of these spheres are in action. As you can see, a lot of processes are happening, and there are a lot of feedback mechanisms which happens between the hydrosphere and the atmosphere when we are talking about land surface temperature or evolution of dust events and how much they contribute to the hydrological cycle and so on and so forth. Development of cyclones or typhoons, like, since it's on that part of the world. So like development of these kind of processes along the ocean cover, land processes. So there are a lot of different kind of mechanisms which are driven by the hydrosphere, and they are affecting the atmosphere, and vice versa. Things are happening in the atmosphere which are affecting our hydrosphere, and so on and so forth. So Earth system science is really about understanding those different kind of complex systems, and we use for that different kind of observations. And this is just a simple animation of the development of some of the hurricanes happening along the Atlantic Ocean. And as you can see here, different kind of observations in different regions of the spectrum. So when we are talking about satellite observations, we are talking about satellites which are able to cover regions from the UV, from the visible, from the infrared, from the microwave, and they give you different levels of information. So this is a microwave imager, so it's giving you three-dimensional water content. And here I'm just looking at infrared channel, giving you some kind of the heat fluxes and how much precipitation is present in the cyclone. And in the background here, you see true color composite or true reflectance. So you can see a combination of different kind of observations over different regions of the spectrum gives us like more and more information about the complexity of that system. Among the things which are really complex, I'm just giving you examples here, a lot of dust events coming from the west coast of Sahara or from the west coast of Africa, and you can see here the evolution of these dust events. And believe it or not, those dust events contribute dramatically to the development of hurricanes that develop over the east coast of the United States. So people who are living in the US are looking into Hurricane Katrina, Hurricane Sandy, and as such, and those kind of hurricanes are driven by tropical systems which are originating from the west coast of Africa. The evolution of these dust particles or these dust storms, they contribute to the genesis, they contribute to the development of those hurricane events. Something like, nobody can think of. Seriously, how hurricanes are driven by dust events from Africa. This is the complexity of our system. like in the recent years, we published a paper in the IEEE transactions. For those who are aware, like engineers, they will know what do we mean by the IEEE transactions. And my co-authors here, Michael Gray and Olga Kalchikova from JPL from Caltech, Jet Propulsion Laboratory, and James Campbell from the Navy. And this paper here, we were looking into projections or cross-sections here of water column in the hurricane itself versus aerosol optical depth or dust particles. And you can see where you have a lot of rain, a lot of deposition, or a lot of genesis, you see some kind of patches of dust. So that explains to you the complexity of our system, the interaction between different spheres, if you will. So I have very arid regions, and I have a lot of dust particles coming from North Africa, and yet they contribute to the hydrological cycle, or they contribute to development of hurricanes. The United States, according to the Wall Street Journal, an article appeared citing here NOAA and citing U.S. administrations, talking about the losses of a hurricane season that was a year of costly disasters. It cost the United States more than $200 billion of losses because of these development of hurricanes. A few years back, I wrote this article in Ahram, and I was talking about global climate change, which we are observing right now, and how much impacts are we observing. So that's this just kind of brief intro is just to make us on the same ground in terms of understanding the complexity of our system and how it behaves. Dr. Delauer mentioned few minutes ago, or in the previous session, he was talking about the global risk report, and some of these global risk reports you can see here. I'm showing you the most important global risk reports. Number one is weapons of mass destruction. But if you check what are the most important risks facing humanity, from number 2 until number 5, all of them are climate related. So we are talking about environmental risks, which are failure of climate change, mitigation, adaptation, extreme weather events, natural disasters. All of these are amongst the most important pressing risks, and all of them fall in quadrant 1 in terms of impact and likelihood. So if you can take a look here, you will see that most of these risks, which are green in color, are mostly environmental basis or of environmental origin. And if you take a look here over the years, starting from 2008 in terms of impact, and in terms of likelihood, you can see from 2008 and 2009, and more green boxes are appearing. And those green boxes are referring to environmental risks. So the most pressing issues right now that we are facing are of environmental origin. We are talking about extreme weather events, failure of climate change, mitigation, adaptation, natural disasters, and as such. And those different fields are on the rise. And nobody really is talking about what might be even happening in the future. Earth observations come into play here. Earth observations have been used in order to address 3 major global agendas and policies, namely climate change action, the Paris Accord, the Paris Agreement 2012, sustainable development, UN SDGs, and the disaster risk reduction framework, the Sunday framework. So it has been implemented, has been used, has been shown how Earth observations can be a vital tool in order to address some of these global actions, and how we are going to show today very specifics related to Earth observations when it comes into play with sustainable development goals. So in my lecture today, I'll try to show some case studies, some examples, real world examples where the SDGs are being assessed by Earth observations, or are being helped in order to really see how we are advancing the SDGs, how we are being able to tackle specific targets. And not only that, but we are going to be talking about the different kinds of tiers, because most of the communities right now are working on very, very basic tiers. I will be able to talk about tier 1, but are we ready to assess some of the tier 2 or tier 3 indicators? That's what we're going to see. So in my presentation, I'm going to be talking about I'm going to be talking very briefly about sustainable development goals, the different kind of challenges, and how Earth observations come into play. And these are some case studies that I'm going to be touching bases on: clean water and sanitation, sustainable cities and communities, life below water, and life on land. And I'm going to also add a little bit about the energy sector. So moving on, if we start talking about clean water and sanitation, which is one of the Sustainable Development Goals, you can see here how Earth observations can be seen as a key for water resources monitoring. Specifically, if you want to talk about indicators like 6.41, 6.42, 6.52, and as such. So I'm being I'm being very selective of specific indicators where Earth observations can really be a tool in order to show, in order to assess how we can measure, how we can target, how we can tackle those different kind of indicators. The transboundary is a big issue that I'm going to be touching bases on following my colleague Dr. Khaled about the GERD and the filling and the drought and the prolonged drought cycles and as such. Another application which will be the sustainable development cities and communities, slums أو العشوائيات, how we are going to be able to tackle those, how we are going to be able to monitor and observe. Dr. Khaled also showed in his presentation some of the urban lands in the Delta region. I'm going to show you how we can build a classifier using AI or using ML in order to really assess the expansion of those different kinds of urban communities. Another application, we're going to be talking about SDG 14, life below water. We're going to be talking about coral reef habitats, coastal electrification, proportion of natural exclusive economic zones managed using ecosystems. So we're going to be talking about a lot about biodiversity and how the impact of global climate change is affecting different kinds of ecosystems. And I'm going to be very specific with coral reefs habitat, how we can use our experience and our available data sets over the Pacific Ocean, for instance, in order to build a global classifier so that I can map what's happening in the Red Sea, or I can map what's happening in the reef of Australia. And as such, we are living in a global community, so things which are happening like in China are not far away from us. We have dusty events which originate in North Africa. They migrate west towards the Atlantic Ocean, creating hurricanes. They migrate east towards the Gulf region, crossing all the way through Afghanistan until they reach to the Himalayas, depositing on the glaciers in the Himalayas, causing a lot of changes into the reflectance of these systems or that ecosystem, and like affecting dramatically the amount of water resources in the Himalayas. A place like the Indo-Ganga Basin, people are suffering from the lack of water resources and the amount of black carbon and soot and dust depositing on those glaciers and affecting their water resources. So the interconnectivity is there. We just need ways of observing or looking into them. Another application here is life on land. Like in our trip today, this morning, I was talking with my colleague, Dr. Bayoumi, and he was mentioning about emissions and like rates of emissions, how we can really be educated about measuring the amount of nitrogen oxides, SOx's, NOx's, pollution in general, how satellite observations, how Earth observations can really show you that, how they can talk about rate of mortality or morbidity or health impacts. So a lot of applications which Earth observations have been a major player. Affordable and clean energy, where we used also Earth observations in order to show the impact on renewable energies. Like we were very lucky to work with the Minister of Electricity and Renewable Energy, and it was just a heartwarming situation this morning when I saw His Excellency Dr. القي, the director or the head of the NERIA, New Renewable Energy Administration, who is here with us today. And it has been a very rewarding working experience the past few years, where we worked together on a project funded by the EU, where we were able to use Earth observations to develop for the first time the Egypt Solar Atlas, and really assess most of the lands in Egypt where we calculated all the different kind of data needed for implementation of solar-based projects in terms of either photovoltaics projects or concentrated solar panel. And right now, that atlas, which was developed in partnership with the ministry, is seen as the official document of the country for different kind of projects. And I would like to invite you all to visit the website of NERIA, and you will see that atlas on the landing page of their website. Challenges. There have been a lot of challenges talking about SDGs in terms of missing data, interconnections, complementary and non-complementary interconnections between different sustainable development goals, complicated and varied problems quantifying and monitoring indicators. All of these are challenges that we have been facing in terms of assessing SDGs. A lot of communities have been talking about in Europe, I attended a few meetings recently, and the failure of identifying some of these kind of indicators. Data and methodology shortage, we have tier 1, 45% of these indicators are supported by both methods and data. We have 39 and we have 16 in tier 2 and tier 3, where they either lack a method or lack data. So now Earth observations come into play. Earth observations can be quite handy in order to address or in order to fill these kind of gaps. However, we still have limited time and we have 10 years only in order to meet our goals, which is not looking like, I'm not pessimistic, but like, a report came out last year, which is the scenario of the 1.5 degrees Celsius. And everybody was talking about that report. That report basically is telling us one thing. If by 2030 we failed to avoid reaching our climate system, reaching a temperature anomaly by 1.5 degrees Celsius, this means that by the end of the century, by 2100, there is no way on Earth that we are going to cap our emissions or cap our temperature by 2C. So the iconic figure, the 2C, which was established in the Paris Accord Agreement, that's in order to reach to that value, we should not by all means touch on the 1.5 by 2030. Right now, the carbon dioxide emissions on our planet already bypassed the 400 parts per million, and there are projections, what we call the RCPs, or the representative concentration pathways. And those RCPs are basically giving you different kinds of scenarios in terms of predictability. So today in the morning, when we heard the term forecast and the term prediction, there's a huge difference, by the way. And there is a myth about our understanding of the difference between between forecast and prediction. And the only problem is we get confused between the term weather and the term climate. I cannot predict weather. I will not be able to tell you tomorrow there is there is precipitation 100%. I can tell you there is a 40% chance of rain. There is a 50% chance. So I will always include a percentage of occurrence in my forecast on a short time event when it is weather driven. But when you are talking about climate, when I'm talking about something by the end of the century, you already have the historical record, you have the statistics of the weather. So you are talking about something which is predictable. I can talk about 2100 and I can say climate prediction, but I can always and only say weather forecast. That's the kind of the misunderstanding between the term weather and climate. So there has been a lot of initiatives, like among those Earth observations play a major role in achieving SDGs, Earth observations for Sustainable Development Goals, EOS for SDG. All of this has been a lot of initiations or a lot of initiatives happening in Europe and being very, very specific. You can see here in different kind of indicators, different kind of goals. You can see here different targets, and you can see different indicators on this table here is showing you where our Earth observations can be handy and how they can be used. So jumping into the first one, clean water and sanitation. And here we are going to be talking about changing trend of water variables, groundwater recharge pattern in the Nile Basin. So I'm going to be focusing on the Nile Basin scenario here. It is not a secret for anybody that by 2025, a lot of people are going to be suffering from water scarcity. We already have a lot of regions, a lot of countries are observing water stress, if not water scarce. And Egypt is one of those for sure. There's no doubt about that. And you can see here, this animation or this map here is showing you something called the EVI, and EVI stands for Enhanced Vegetation Index. It's a parameter used in order to assess the degree of greenness, the degree of healthiness. And what you are seeing is just an anomalous behavior. So I'm just showing you increases and decreases. I'm not showing you time series data. I'm not showing you any kind of data. But there are challenges. There are challenges in terms of physical challenges, natural challenges, and at the same time, some kind of constructions. And this is the animation of the GERD over the past few years, seasonal variability, where I'm also showing some inundation, some flooding events here, or some impact of water increase. Water stress in Africa, all these countries in red are already water scarce, and here are water stressed. And this is the water demand in Egypt according to the FAO. This is pretty old. 2011, it was mentioned that 80-something% of our water resources are being used in vegetation. I would assume that it is a little bit less now. It's like above 75%, I would say, used in agriculture, and the rest will be in domestic use and other resources, but still, very, very high value. But that's the thing. It's very important to understand what do we mean by the water scarcity. So right now it is defined by less than 1,000 meters per person per year. I believe that we reached it already like close to 500 something in Egypt, which is really like not a very pleasant situation. So what should we do? We should be very careful with water budgeting. Of course, I'm not going to go into a lot of things here, but like the whole system here is showing you the balance between the energy system and the water budget. So what I'm showing you here, how we can account for water resources, how you can measure, how you can assess the water usage in terms of precipitation, in terms of evapotranspiration, in terms of runoff, so that you can really assess how much water storage you have in your system. So these are different variables, and all of these variables, if you will, soil moisture, precipitation, evapotranspiration, transpiration, runoff, all of these can be assessed, can be measured using satellite observation. So basically, we can end up having quantified system. You can really actually quantify on the ground how much water is being, or how much is being implemented in all of these variables, so that you can have a very good educated guess about your water storage. I'm comparing here the Amazons versus the Nile Basin, and you can see here a little bit of departure between both curves. One of them is basically giving you the input, which is the precipitation, evapotranspiration, and runoff, and the other is showing you the water storage anomaly, which is on the decline. And I'm going to come back to this in a little while. I'm going to be skipping some of my slides, or like I'm not going to overwhelm you with a lot of details. I'm just putting some techniques or some data just for the sake of completion and credibility, but I will not be tiring you with a lot of technical information. So here's the sources of the data, like coming from where, what are the different kind of sources, or from where we are getting these data sets. And when I'm able to do that, we are able to assess terms like this: precipitation coming from TRIM, tropical rainfall measuring mission. It's a microwave imager. So I'm able to assess the amount of precipitation on monthly basis over the past 10, 15 years. So basically what I'm showing you is the TRIM composite climatology. And by the term climatology, I'm showing you the anomaly, the behavior. So I'm getting the average over the past 15, 20 years, the lifetime of TRIM over Africa. But now let's focus more on the Nile Basin, and as you can see here, how the precipitation anomaly is behaving, how it is changing along the Nile Basin. And here you are going to see some different kind of variables. So I'm talking about precipitation. And again, it comes back to the same equation that I mentioned before, where we want to assess, we want to measure those different kind of variables. Going into evapotranspiration, so you can really measure, you can quantify the amount of evapotranspiration. One of the very important missions that was launched on the space station right now, it's called EcoStress. And the EcoStress is the latest, like it's the state-of-the-art system, where right now it's able to give us observations twice a day. In other words, you can quantify how much water is needed for irrigation by the field, by every single field, how much water is needed, because you are able to calculate evapotranspiration twice a day. So you don't over flood like all the different kinds of fields with water. No, you will be targeting specific areas which are under water stress or need water. Vegetation, the previous one was soil moisture. So you are able to assess these different kinds of variables along the entire basin, and that will help you to have a good educated decision support system. So looking into the different countries in the Nile Basin watershed, so this is the entire Nile Basin watershed, and you can see here the migration between the two variables. So one of them is again the PER, and the other is the water storage. And when it comes to Egypt, you can see here the declining trend, and that declining trend is a very good indicator of the overwater exploitation of the underground water resources. So really, like, you know, if you can take a look here, starting 2008, 9, 10, 11, and as such, so we are on a decline here, which is not very good. When I'm comparing with Ethiopia, I see a lag. There is a little bit of lag, which also is a proxy about like the different kind of soil and the different kind of lithologies in these different areas. Some areas are showing like an increasing trends, and others are showing a declining trend. And you can do a lag analysis. Basically, you can see how much month it needs for the infiltration, so you can really assess some kind of soil parameters as well. How this is helpful, because now you can target like, you know, specific tiers like this change in water usage efficiency over time. Another indicator here of a different tier level, which is level of water stress. Tier 3, indicator 6.52, proportion of transboundary. We're going to talk about that in a minute. Tier 3, another tier 3 indicator, which is change in the extent of water-related ecosystems over time. So using Earth observations, you can really assess something like this. In 2012, NASA showed this map coming from something called GRACE. For you who are aware of GRACE experiment, it's a gravity-driven satellite platform. So it doesn't work with electromagnetic spectrum, it doesn't work with sunlight, however it works with the gravitational anomaly, which is basically a representation of mass. So I have bigger mass, which will give me a bigger gravitational anomaly or gravitational attraction. So when you have a change in that mass, which is a proxy for recharge or discharge of underground water, you can see this kind of anomalous behavior. So you can see these kind of dark spots over Egypt, which are representation of the lack of the water, underground water, or the retreat in the amount of the recharge that we have. And of course, like Southern Europe and North Africa, all of these regions are under severe water stress. But not only that, we have other global phenomena like El Nino. Some of you might have heard of El Nino, which stands for El Nino Southern Oscillation. So El Nino is a global phenomenon. And El Nino is a phenomenon which develops as a consequence of the migration of warm water in the Pacific Ocean. So you have a lot of warm water on the west coast of the United States, and this warm water in the tropical region, they migrate with the trade winds. They migrate from the west to the east, crossing the Pacific, causing a lot of issues in the upwelling and the cycling of the nutrients in the ocean. And when they move to the west part of the Pacific Ocean, they cause instability and like a kind of irregular system, and then they move back again. And this motion, we call it the interplay between the warm waters and the cold water. They result in a lot of extreme events, and those extreme events can be extreme precipitation or extreme droughts. So they can cause a lot of rain in some areas. So the impact, so the change is global. The climate change is global, but the impact is local. And this is where the term glocal came from. If you heard of that term before, glocal, which is the global impact on a local scale. And this is exactly what's happening. So you see El Nino will have wet areas, but even in Africa here, you will see wet parts, but you are going to see also dry parts. So if you take a look in Central Africa and in Ethiopia, where the dirt is being built, there is a huge dry impact on that region as a consequence of El Nino. But at the same time, in the same country, different area of the country, you are going to have a huge wet season. So you are going to be seriously, I have a lot of dry weather in some place of the country and I have a lot of rain somewhere else. Yes, this is what we mean by extreme weather events. This is what we mean by global warming or climate change. Something similar, because things are quite global. So here in California, we were able to use data mining and machine learning in order to assess El Nino in California. And this work here, I'm not going to go in much depth, but we have machine learning techniques, neural networks. We used convolution neural networks and recurrent neural networks. And you can see here two curves, a gray curve and a dark curve. So the gray is observed, is data that we have. And the dark one is what we forecasted from our model, from our machine learning model. And you can see here, 1997-98 was a very, very wet period for California. It was massive amount of rain and flooding. And here, our model did an amazing job. It was comparison with the observed data. And we can see here a lot of matching. But here, in 2015, 2016, everybody was expecting a very wet El Nino season in California, which did not happen. So our paper here that we submitted to that journal, early on, so here you can see we stopped our observations because we don't have observations. So this is only our forecast. And our forecast was showing a declining trend, and it's very, very dry. And you can look into our error bars here, which is a proxy for accuracy of the model. So you can see here that for the first month, we have very, very high accuracy. It was almost 70% accuracy in terms of matching between models and observations. And the paper was submitted in March 2016, and it got published January 2017. So it stayed under review for 9 months. Basically, they were waiting for the El Nino season to pass because it was kind of very interesting to show, like, it's dry weather during that time. So there has been a lot of talk about El Nino and how it's going to affect African countries, and they are urged to prepare for the rise in extreme El Nino events. How we can see that? We can see that from data, from precipitation, soil moisture. So Dr. Malak today in the morning was talking about learning. We here apply learning, but we say data learning techniques instead of data processing techniques. So we are learning from our data in order to apply that. So using some kind of data learning techniques, I'm going to show you some really interesting results about precipitation in the Nile Basin. So here, a time series for different countries in the Nile Basin. Here focusing more on soil moisture. So this is precipitation, this is soil moisture. But here I'm going to be focusing on 3 major countries, Sudan, Ethiopia, and Egypt. And as you can see here in the period, and this data is coming from a sensor which is called SMAP, like very, very well, like famous sensor on board of one of the missions at NASA. And SMAP operates from 2010 to 2018. So this is the amount of data that I have. But I have other data sets from other different locations. But from SMAP, it showed us in the years 2010 until 2012, you see here there is a massive decline in soil moisture. We don't have a lot of soil moisture, which is a proxy for precipitation. So basically you have very dry period. But over here, until recent, which is happening 2018, 2019, you have kind of a wet period. Oops. You have a wet period, right? And then we are gonna see how this, like what does this mean? In the negotiations that we heard with our colleagues and friends from Ethiopia, like, they identified the meaning of a prolonged drought. So that was their explanation of what do we mean by the term prolonged drought, based on the Blue Nile annual yield, billions cubic meter. And they just looked at several peaks, which are the low. This is not my data, by the way. So I just got this data from what was presented by Ethiopia. So this time series here is showing you the Blue Nile yield, and based on their observations, they just highlighted 4 different years, 4 different specific years that they called as the very, very dry period. And based on that, they just drew that line, which is identified as the minimum allowable flow, like to the countries in the north during the drought periods, which is basically 31 or 30-something BCM, which is basically like, if this is what we are going to be getting in Egypt, so basically it's like, the end of agriculture, the end of life, like it's going to be a mess. So basically, like, long story short, this cannot happen. Like, if this is the limit or this is the line at which we are going to be getting the yield, so this is a really big problem. And Earth observations can show us how we can really talk about a target like this or an indicator like this, proportion of transboundary basin water cooperation, how we can cooperate in order to understand something like this. And by the way, in this time series, this is 1913, so this is 14, 15, 16, 17, 18. So this trough here is 1918. Which was not highlighted by our colleagues, but 1918-19 was a very famous El Nino season, like, highlighted by the American Meteorological Society. It was a remarkable year in terms of droughts. There are a lot of research showing that by 2025, 2050, some countries, including Ethiopia here, will be moving from water stress into water scarcity. So by 2050, there are a lot of projections showing that these countries even will be water scarce, which plays a major role in, like, the amount of water that we are expecting, and also like periods of filling, periods of operation, all of that we can talk about. So let's take a look, into this time series. I'm not going to overwhelm you with a lot of techniques, but I'm just going to touch on them very, very briefly and very fast. And by the way, Dr. Marwa, I'm going to put you on the spot here. She gave me 45 minutes. I'm not sure if this is going to be workable or not, so I'll try to do my best.
We have 15 minutes.
We have 15 minutes more? Okay. I did not even finish 1/4 of my presentation, but that's fine. I'm going to manage. I'll manage. Maybe I'm just going to focus on what I can right now, and then I'm going to cut the other parts short. So this is the precipitation time series that we have from Ethiopia, and here, this is the anomalous behavior. And by the term anomaly, we are talking about the deviation from the norm. So basically, you have an increase or a decrease. So somebody might say, do you have something called negative precipitation? No, this is anomalous behavior. In other words, you get the average, you subtract that average from the observations, you divide by the standard deviation so that you can have normalized kind of behavior. So you can really see how the time series is behaving. We applied something called Fourier transform, like not to make this very technical, but it's a way of looking into the data in order to understand something very important. And that's the key of my issue here, which is understanding how the physical system is driven. So when I talk about precipitation, there are a lot of global circulations which are driving this system. So precipitation is not only data that you observe every single year. Yes, you can see a season. So from January to January, you know that January is going to be a lot of rain. The following January is going to be a lot of rain. But you cannot, by all means, say that you know how much rain is going to come the following January and so on and so forth. So even the seasonality, you are not able to talk about the extent or the magnitude of the event. Not only that, but I'm talking about something totally different. I'm talking about the frequency of the event. There are a lot of physical systems driving the hydrological cycle. It is not only seasonality. There might be a Nino cycle, which might be happening at a different time period. There might be decadal oscillation. There might be a biannual oscillation. There might be a 6-month cycle. So I'm talking about different cycles embedded in the system, which might have totally different frequency of occurrence. So right now, the idea is how we can identify those cycles and how we can see which one of them is the most important driving your hydrological cycle. That's very important. Here, it's showing you seasonality is a big frequency, of course, because it happens every year. But when you come into something like this, so here we apply something called empirical mode decomposition. This is really showing you the intersection between data sciences and Earth observations, where, like, you can really drive very complex information from that system. So what you are seeing here are basically frequencies variabilities. So I'm looking into anomalies. I'm looking into seasonality. I'm looking into decadal oscillations. So each one of those figures is a representation of a physical system, of a physical phenomena at a different frequency. Something might be happening every 10 years. Something might be happening every other year. Something might be happening every 6 months. And so I'm talking about the frequency domain. I'm not talking about the time series per se. So, and this is very important because when we are able to do that, we are here interpreting what we call intrinsic mode functions, which each one the change in amplitude and frequency over time, reflecting the evolution of the physical process over time. So basically, I'm looking into the physical process which is evolving over time. Long story short, so what are we learning from this? We are something else called Hilbert-1, which is showing us those different frequencies, but you can see the curves are having different kind of weight. Look at those curves here. In different parts of the curves over the whole time series, some of them are showing darker, some of them are lighter, some of them are fading out, some of them are getting bolder. So in other words, in every single time frame, you are looking into what is driving the physical system there. So I might be getting a lot of rain this year because of seasonality, but I might be getting a lot of rain next year because of El Nino. But I might be getting another stronger precipitation the following year because of the PDO, the Pacific Decadal Oscillation, or the AMO, the Atlantic Oscillation. So now you are looking into what is really driving that system. And this is very important. Why? Because when we looked into the El Nino cycle, this is the frequency of El Nino, and see how much it matched between the precipitation cycle of Ethiopia. So basically, what we are concluding from here, that the climate system or the precipitation cycle in Ethiopia is driven by El Nino. In other words, El Nino will have a dramatic impact on that precipitation cycle. And this is shown by the frequency analysis. I'm not talking about time series, I'm talking about the frequency components embedded in the time series. This is very, very important. We did the same assessment for the 3 countries, Egypt, Sudan, and Ethiopia. Of course, Egypt is suffering dramatic droughts here. But also in these other countries, you can see like those colors are a representation of the accuracy of this kind of correlations. So going back again to the soil moisture curve that I showed you at the beginning, so you can see here very, very, very dry periods, which are very obvious. But over this area, you can see a wet period, which we are observing. But this is, within this wet period, there is nothing wrong with observing some dry years. So I have a wet period, and included in this wet period, I have very, very dry or scarce years. So that's very important to understand how the system, which means that in these 10 years, we have been observing a wet period. So what is going to happen next? So based on that, like, you know, we are starting a new cycle, 2019, 2020. So I would argue, based on educated guess, I'm not like just throwing out predictions, but based on data, based on observations, based on data analysis and frequency analysis, I would say that starting 2021, it will be quite dry in these areas. So that's going to be a very important component in the negotiations and understanding the prolonged drought. So this is the curve again, the curve that I got from this data, and these are the representation of my analysis. So my findings were that this years actually happens to be El Niño years. So those years identified in this data, when you check them out, and this is public record, you can always find that those specific years are very severe El Niño years. And those years are not the only El Niño years. However, all these circled years that I'm doing are also El Niño years. So it is not only those. However, these are all also El Niño years. So based on that, now my line is rising a little bit higher than that proposed line. So my proposed line now is around 46 billion cubic meters. So basically, that is my definition of prolonged drought. So it's totally different story, like, you know, from starting at 30-something, and actually after doing the data analysis or looking into these observations, this is the actual representation. So I'm gonna be moving quite fast. You can stop me anytime you want. So just like tell me, Hisham, get out of here. So I will just move. So moving into another indicator, sustainable cities and communities. It has been on the rise. Like, you know, the urban development is rising in different countries, and these are some of the projections by 2050 in terms of expansion and sometimes regulated or irregulated expansion. We are using impervious surfaces, which is one of the indicators in the Sustainable Development Goals, and this is the definition. They are mainly artificial structures such as pavements, roadside walkways, driveways, parking lots. All of these are areas where water cannot be penetrating. So you are using this kind of information in order to assess how much impervious surfaces we are having or how much unregulated urbanization is happening. We don't have data on the ground to do that. So what did we do? We used data from the US. We used some kind of databases where we are training and we are evaluating. So all these red boxes, we are getting actual data from the ground to train what do we mean by impervious surfaces. And then we apply our model or our classifier on these blue regions in order to evaluate the accuracy of our model. And you can see here, root mean square errors are dropping by time, so it is really learning very well. Applying this on different countries in the Nile Basin, you can see here in Addis Ababa, 2013, this is the satellite image, and this is our classifier showing you the level of urbanization from 2013 until 2019, and see how much matching between the actual satellite image and the classifier being able to highlight or identify impervious surfaces. Same thing in Cairo. This is 2013, this area here, which is classified by our classifier, and this area satellite image. And you can see here the expansion. However, our classifier is not perfect. It's not able to identify spots like this. So this is an area where you have urban development, but our classifier failed to find them. Why this is happening? Because we are training on data coming from the US, which is a lot of, like, you know, sometimes the land use, land cover is different from what we are having in our countries. So that's why you need to have local classifiers. You need to have data here, and that can be a very important project where you can really map. It's just a matter of, like, you know, getting some spectral information about the different kind of surfaces you have here, so that you can really have educated classifiers. Same thing applied in Sudan and Khartoum. Here I'm showing you the expansion. Not only these are different slum areas in Cairo. Dr. Khalid was showing this morning, some urban areas, but here we're even showing you the expansion using our classifier, which can be applied globally. Not even that, but we also were able to highlight a very slum area here in Karachi, Pakistan. And actually this paper has been submitted to a very prestigious journal and a specific issue about Earth observations for SDGs, and the paper just got accepted a couple of days before yesterday. So like 3 days ago, which is good. So I'm happy that it has been accepted with revisions. We have submitted our revisions, and we should hear back very soon. So again, how this is helpful, because you are able to talk about specific indicators, proportion of urban population, ratio of land consumption rate to population, proportion of population living in cities that implement urban and regional development, and so on and so forth. So you are able to touch on specific indicators with different kind of tiers, and this is important when it comes from the perspective of planning or meeting the SDGs. Sometimes we fail on assessing different kind of SDGs. Another indicator for pollution, using different satellite observations, where we can talk about like oxides in general, and you can assess levels of mortality or morbidity. And this is TROPMI. This is one of the very famous sensors, which are current sensors, and you can see that on the MENA region. We are doing some kind of regional analysis, just correlations between different variables, and a couple of papers got published this year also about like different kind of trends. Here, urban health-related air quality indicators over the Middle East and North Africa, and one here which is more about aerosol variability over the greater Delta region with some colleagues here from Egypt. Again, touching on a specific, very specific indicators, mortality rate, annual mean levels of fine particulate matter. All of these are variables that you can quantify using different kinds of Earth observations. Life below water, coral reef habitats. A lot of corrections that needs to happen in the data. This is something called water column correction. One of the work that we did over Hurghada a few years back, showing you like mapping of different coral habitats in Ghana, and just showing you a map about 1985 here. This is the coral habitats, and this is mangroves, Gifton Island. Look at this spot here. I want you to take a look from 1985 to 2014. Urban development. These areas here, like the change in that color represent a massive impact on the biodiversity. So speaking of the biodiversity in the morning, this is something very important here. And this work actually has been highlighted on the NASA Earth Observatory and was chosen as the image of the day back in the years. So using that, we started working on different islands in the Pacific, and we created our own global classifier. These are different stages of the data manipulation and the data interpretation, the training of these classifiers, applying it on different kind of regions, where we assess the accuracy of our models on different islands, Palmyra, Atoll, Howland, Baker Island, and Kingsman Reef. All of these are islands that we have ground observations and we have satellite data. So we are learning, we are training our models, we are training our data, so that when we apply it on a different two islands, totally different islands, we are able to identify that. Also, it has been highlighted on the Landsat science domain as one of the interesting research. And then we are applying this right now on the Red Sea, and we have some very, very interesting results in terms of mapping coral reef habitats in the Red Sea here. I don't want another application for life underwater, talking about chlorophyll content and the nutrition cycle in the Red Sea, what kind of algal blooms that we have in the Red Sea, talking about deposition of dust particles, talking about cyclonic behavior or nature of cyclones. I'm skipping a lot of slides, but here you can see the dust particles coming from the eastern desert and affecting like this cyclonic behavior in the Red Sea. You have patches like this in the Red Sea about chlorophyll content, harmful algal blooms. So sometimes we hear about nutrition, we hear about lack of nutrition, and as such, it's happening because of things like this. So long story short, there are a lot of work that we have been doing using Earth observations in order to assess, in order to tackle specific SDGs, in order to highlight them. I wanted very briefly, but probably I don't have time, so I'm gonna stop here. So this is life on land. I wanted to show some kind of work on mangroves, and then I was gonna end with solar, and I don't have time to do that. But anyways, long story short, that Earth observations have been utilized in order to address specific indicators, specific targets along the Sustainable Development Goals, and it proves to be quite useful and helpful. Thank you so much for your attention.
Thank you, Dr. Hisham. I know that you have a lot of data, and it's amazing the amount of data these models are able to generate and to give us a lot of insights and information about our environment, our systems, and the phenomena, and that's very important in any work that we need to do in the future and to move forward, and also to assist with the decision-making process itself when it comes to issues related to sustainable development. I'll open now the floor for a few questions, and I hope that they would be like questions rather than comments, because we're coming to an end today and we need to wrap up. And Dr. Ismail.
One, during the exposition on the library, in history, he said that we stopped at Anwar Sadat. Where are the rest? The rest. Where are the rest?
وهل المكتبة قبل ما حضرتك ترد إن مفروض الأمور فيها politicized يعني هي مفروض إنه science.
Well, supposed to be well, actually, the library is supposed to provide science and information rather than not mingled with politics or politicized. So I'd like to listen to your questions, how to respond to these. شكرا.
هل حضرتك يعني بتشير ان امكانيه استخدام الداتا اللي هي موجوده عن
data? You mean that we should use data on Abdel Nasser, on Sadat, or what? No, we want a similar archive on Hosni Mubarak and others. Why particularly President Abdel Nasser and President Sadat?
بس عايزه اوضح انه يعني اللي عرضه المهندس يوسف هو مجرد يعني نبذه عن اهم البروجكتس مش كل حاجه.
I'd like to say that there have been a lot of more enormous work not exposed by Dr. Yusuf, because there has been a full archive on the memory of Egypt showing all details and narration, everything. We've been working on a lot. Hosni Mubarak, and well, this only a sample. We didn't want to consume your time, to use up all your time. Just using technology, what we just provided samples of what the library has been doing. Well, what has been presided is only 1% of what I've been doing. It takes a lot of time to build an archive like this. It can't be built overnight. In future, we do hope that the library is going to produce more.
Question to Dr. Askari. طبعا you need a whole session, Doctor, so that we can concentrate. I hope that we will have such a session in details. My two questions are the following. What about the lobbying, actual lobby against climate change? Last year, in the United States only, more than $900 million were in research, think tanks, meetings, conferences against climate change, supported by a lot of multinationals, supported by some politicians, including Mr. Trump, including the Republicans. So this is a very strong movement with its research paper and so on. I don't want to mention names of those prominent even societies. This is my first question. Second question. Scientists, Nobel Prize scientists, have gathered a lot of times. If we do reach 4 degrees centigrade, if we do reach 6 degrees centigrade, and those possibilities have been made, actually, could we inject particles of water so that we, against 45, 50, 60 degrees temperature of the sun? Or some scientists, Nobel scientists, have proposed sulfur, like volcanoes, so that to have this. So what about those two different opposite movements, Dr. Askari?
Okay, So before Dr. Askari replies to this question, I have to mention that he has a lecture open for public on Tuesday at the Library of Alexandria at 3 p.m., 10th of December, and you're all welcome to join us for more details and maybe to have more time to ask other questions and discuss other matters related to his work.
Thanks, Dr. Sharif. 2 points, taken very well. I agree with you. There is a lobby against, understanding climate change, or they are not believing in climate change and calling climate change myths and stuff like this. But it is not a big lobby. I can agree with you that there are some voices out there, but it is not scientific. It's more political driven, and how it works. President Obama, one of the very famous climate activists, and he was a big advocate for climate change. At the time where he was advocating for climate change, he was signing agreements with Shell in order to start their exploration of oil in the Arctic regions, and in some areas where you are really talking about permafrost and keeping massive amount of methane. So when it comes to politics, which is not my game here, versus science, which is what I'm talking about, there has been a lot of evidence about climate change, and it is not deniable. It is not some people might be talking about a natural cycle, and I have no problem with that. We have observed the 2 degrees Celsius increase over the past thousands and millions of years, but I can tell you that there is no record whatsoever millions of years ago that CO2 ever exceeded 350 parts per million. That's my argument for you. So the counter argument would be, yes, there is a natural component. Yes, the solar cycle plays its role, but never on Earth, never on this planet, according to different kind of isotopes, different kind of paleoclimatology studies, it was never recorded that CO2 exceeded 350 parts per million or 300 something parts per million. Nowadays, right now, it is beyond 410 parts per million, and it is foreseen to exceed. When you talk about different kind of scenarios, the 6 degrees Celsius, the 7, the 8, and as such, these are extreme scenarios, and everybody can say whatever they want about those scenarios, because basically nobody's going to be around. If the temperature of this planet increased by 7, I'm not talking about temperature anomaly. I'm not talking about temperature increase in Egypt. No, I'm talking about a global temperature anomaly. When I say temperature anomaly by 7, it means that Egypt can increase by 20 or 30, and the Arctic regions can drop by 15 or 18. But when I'm talking global temperature anomaly increase by 7 degrees Celsius, you are talking about the end of time. At 4 degrees Celsius anomalous behavior, you are going to find extent of 50% of the human species on this planet. And this is not sci-fi. I'm talking about things that we observed in our lifetime. All of us saw what happened in Sumatra. All of us saw what happened in the tsunami in Japan. One single event taking the lives of more than 250,000 in just a blink of an eye, right? One event taking massive amount of lives. So global climate change or global warming, it is not about the increase in temperature that we are observing. It is about the magnitude and the frequency of extreme events. Global warming not necessarily means that the temperature in Egypt is going to be rising all the time. No. We observed a few years back in Cairo some glaciation periods. I wouldn't say glaciation, but like there was snowing events, right? There was ice, there was snow in Cairo, a tropical region, hyper-arid, and you have snow in Cairo. This is unheard of. But this is a sign for global warming. It should not be taken against global warming. No, global warming is about showing you extreme events. It can be extreme warm, it can be extreme cold. That's the idea of global warming. When Trump's talk about the politics, that's totally fine. But when it comes to actual budgets, NASA did not suffer any kind of budget cuts in their funding. The NSF, the National Science Foundation, did not suffer any kind of budget cuts. The Department of Energy did. Yes, I agree with you. The Environmental Protection Agency, because of the lobbying and because of the politics. So again, global climate change, there is a lot of political will that our colleagues talked about today in the morning, and also it is a matter of I don't know the term, but it's a personal decision as well. Global climate change adaptation is not cheap. Nobody is saying that we are going to pay a small bill. No, there is a big bill for global climate change adaptation. So I hope I addressed your comments here.
Thank you, Dr. Hisham, for your valuable and important presentation. My question is, I have a couple of questions, actually. The first one regarding the drought that you're expecting in Ethiopia in year 2025, and what have you seen in the coming year from 2020 to 2025? This period, what do you expect, or what did your findings show? And how long is this drought going to be for, that is starting in 2025? The other thing is that some scientists who have prepared a report some time ago called the NIPCC, the non-governmental IPCC, we're talking about a warmer climate might be better for the world, things like this. But they have mentioned something like the increase in rainfall, some warmer temperature that's good for some of the species. But here I'm interested to know whether any of the studies have shown that the volume of precipitation, I know that there will be extreme events, some areas will be drier, some areas will receive droughts or show droughts, some floods. But I'm interested in the volume of rainfall. Is it going to increase or decrease? Because I've seen a presentation by one of the climate change scientists indicating that the total volume is going to increase. And I just want to confirm from you if that's a true finding or not. Thank you.
Thank you so much for your questions. Regarding the first one, about the years of droughts. You agree with me, and I think any scientist will agree that there is no physical phenomena which is a perfect sine wave, right? When it comes to the word of climate or the word of prediction, we want to see, by the term cyclic, by the term sine wave, I mean cyclic event. So in the world of data, I'm dealing with data that I'm claiming it is non-stationary. And by the term station, I mean that you know for sure that every single year something specific is going to happen. This is data stationarity. But you are not talking about data. There is absolutely no way that you can say any of the physical systems are stationary or can fit a perfect sine wave. So that by default would take out of the equation when we say how long it is expected. So the term, that's my argument against the idea of filling period. You cannot say I'm going to be filling in 1 or 2 or 7 or 10. You cannot say that because you are, by mentioning a period, specific period, so you are claiming that your data is stationary, which is not. So you by default are assuming something which is wrong, okay? So that's why what I'm claiming or what I'm saying here, that the filling should be related to the hydrological cycle. I have no problem to fill it in 1 year. No problem. That's fine. You have enough, fill it. But you have to tie it with the hydrological cycle. Talking about extreme events, and I know the article that you are referring to, which appeared in The Economist, correct? That there was an article coming from renowned scientists at talking about extreme events and causing a lot of flooding in Ethiopia, and actually GERD is going to protect the whole basin from flooding events. Yeah. But do you know what scenario was used for that assumption? The RCP 8.5. And the RCP 8.5 assumes that the CO2 concentration is going to be 935 parts per million. And I'm giving you specific numbers. You can very easily go and check what I'm saying. Check RCP 8.5. And that was the scenario used in that article you are referring to, which is saying that there will be massive amount of floods. The RCP 8.5 means that the temperature is going to increase by 7 degrees Celsius. So nobody's going to be around to assess how much flooding is going to happen. Yeah, there will be a lot of flooding, but it will be end of time. There will be no life on this planet. There will be maybe fungus, there will be some kind of microbes, if even they are there. But when you are talking about RCP 8.900 parts per million carbon dioxide, this is the scenario which will bring you a lot of flooding. This is the scenario which is basically gonna have an end of time. Referring back to Dr. Delauer's comment about sulfates and all of this, There has been some talks about that, initiating a lot of water droplets from the Pacific Ocean, having fleets of ships pumping massive amount of water from the ocean into the atmosphere. Do you know what's going to happen? When you have all of that, all the water will evaporate, and you end up with a lot of sulfates, a lot of salt particles. And those salt particles will act as what we call cloud condensation nuclei, creating a lot of cloud cover. So basically you have a lot of clouds which will act as, with their very high reflectance albedo, they will act as a blanket reflecting a lot of solar energy, a lot of solar radiation coming from the sun back to the atmosphere, and which will end up in cooling your system. Sulfates happens, volcanic eruptions, they induce sulfates, and it has been recorded in the historical time, every single volcanic eruption that happened over the geologic time was followed by glaciation period. You have volcanic eruption, you have glaciation period. It has been recorded in the history. So yes, but all of these are artificially introduced to the system, which cannot be used. But back again to Dr. Khalid, to quantify the amount of water, you cannot do that because you are talking about anomalous behavior. And so I cannot preach for something that I'm saying you cannot. Like when you are talking about a weather-driven phenomena, you cannot predict it. When you are talking about a climate-driven phenomena, yes, you can. So I can tell you the drought periods, but I cannot tell you how much rain is going to happen. Make sense? Yeah.
We have some questions. عشان اليوث يعني just we take some voices from the youth first and then
I'm Khalid Al-Gamasi, a molecular biologist at the Faculty of Science, Alexandria University. I would address 2 points. You mentioned was using the Earth observations to assess the sustainable developmental goals. You talked about the mortality rates and the increase of urbanizations. Is there any studies that you have done or being made in the field with, multidisciplinary fields between the change of climate that gonna impact the change of epidemics, like maybe upcoming disease or something? And my second point, I'm kind of interested in the field of astrobiology a little bit. So in about 1 billion years, the sun is gonna increase its intensity about 10%. So all of the ocean on Earth will evaporate, and well, Earth will not be in the Goldilocks zone. So what is like a great informative scientist as you are? What are your thoughts that our species as a human, if we passed this century with all of the mess we got from the climate change, would be space explorations, or would we have the power to terraform Earth or move to another planet? Thank you so much.
We are not moving anywhere. Thanks for the comments. For the first one, yes, we did some work related to the valley fever outbreaks in Arizona. In Phoenix, Arizona, it's massively impacted by what we call haboobs, dust haboobs. And we have a couple of papers about that, about the different kind of spores and fungus that originate from the ground, like causing valley fever outbreaks, epidemics, as you will. So yes, we did some kind of work like this. And actually, I was quite lucky and honored to work with Dr. Magdi Yaoub on a research article that we published together, believe it or not. He's a world-renowned cardiologist, and I'm just an earth system scientist. And in one of our meetings, because I worked closely with Dr. Yaoub, with His Excellency Dr. Khayat on the project of Aswan, to have their power, like to have the new hospital, inshallah, running by solar. Like he's like a visionary guy, and he really wants to be sustainable and green. So we did a plan. We met with Dr. Khayat, we met with His Excellency Dr. Shakir, and we put a plan together. But during my conversations with Dr. Yaoub, he was talking about something, and then I mentioned to him, I work on Kawasaki disease, and that term, intrigued him dramatically. Kawasaki disease is something which causes heart arrest for kids, and it's an epidemic which is mainly driven by, believe it or not, climate. So you will have different kind of fungus, microbes originating in the highlands of China, and then it moves all the way to Japan, and then crossing the entire Pacific, and make a landfall in San Diego. And believe it or not, there is a center for Kawasaki disease outbreaks in San Diego. And me and Dr. Ya'qub, we started working together on this because we figured out how come that fungus is able to survive the UV radiation for 6 days. احنا بنروح لدكتور أسنان, when you go to a dentist, you see that everything is just put in UV in order to kill microbes. So how come that fungus is able to survive, like, for 6-7 days to migrate across the Pacific? And guess what? Dust particles were protecting that fungus. So the fungus will be like hosted by a dust particle, and the dust particle will do a lot of scattering, which we call the Rayleigh scattering scheme, which happens in the UV region of the spectrum. So the dust particles scatter all the UV radiation, protecting that microbe to survive, to cross the Inter-Pacific. And we published a paper in a journal called Global Cardiology, Science and Medicine. So a paper in remote sensing is published in that journal with Dr. Ya'qub as a co-author on the paper. So that was very interesting. Regarding are we going to leave this planet? We cannot. One of the Nobel laureates that just, an article just appeared yesterday on the ABC, you can check that. One of the new Nobel laureates, he was talking about, there is no way on Earth that we are able to survive in another galaxy or in another, out of space. So all of these kind of talks are just for fun. People are just saying it. So instead of thinking about that, let's fix our planet. Right now, we are heading toward what we call, Dr. Khaled even used it in his presentation, the Anthropocene. And this is the new time where humans are really impacting our system. And it is not stable. So we have a problem that we have to admit to, but there are ways that we can address it and try to fix it. So, yeah.
As a microbiologist myself, I have to tell you that microorganisms have amazing abilities and they can survive a lot. So I'll have to wrap our discussion. I mean, we have a second day and we're all around. If we can talk later about these and stir up more discussions, but just to wrap things up as we're past 6. So I thank our panelists and I thank you all for being here for our first day, and I hope to see you tomorrow with more enriching and more vivid discussions. Thank you all.